Hi, Eric. My name is Ludmila. I'm the chair of the department. So thank you so much
Thank you for
for,
coming. Yeah.
yeah, well, I mean, the students made an incredible selection. So we're really glad to have you here.
Yeah, no, it's quite an honor. And I also understand this is the first in-person one, you know,
Yeah,
wow.
so it's a big deal.
More pressure.
Thank you. This is a big deal, especially for the students, right?
Yeah.
And I know that they organized with a lot of care.
Yeah, I can tell. Thanks for having me.
Thank you.
New faculty joined in
Oh,
September.
Okay.
Actually, nice to meet you. I'm actually right next line.
Oh, really? I sent her a picture of you in her office. So.
Yeah, she's awake. Yes, you know that, right? So, yeah. But thank you again for coming, and I hope that you continue to have a great visit.
Yeah, it's been so much fun.
Okay.
Yeah. And the weather turned out.
Okay.
That feel like working.
Excellent. So you got to know more of the students. So it's like for this event, we pretty much dedicate for the students to have more opportunities.
Yeah.
With the, you know.
Wonderful.
Yeah. But,
Oh,
I think,
yes. I met you only when I was a postdoc at Penn. I only met you virtually like on Zoom during like the first orientation of the year or something.
What year was it?
2021.
already.
It's like a blur.
But no, it's good to see you.
Doesn't it look like that? We forgot.
Yeah. And we try not to remember.
Yeah. Are you guys back to normal?
But the tool is more from particularly the Department of bringing to typically works. So we have like like a food truck and then it makes breakfast for everyone. People show up.
Hi, I'm going to be introducing you.
Oh, okay. Nice to meet you.
Nice to meet you.
We haven't met before.
We haven't met before. I'll be having, I think, lunch and dinner.
Wonderful.
Excellent.
Wonderful.
Yeah, I got my house down, so have a great visit. Thank you again for being here.
Oh, nice. Thanks for having me. Nice to meet you.
What's your visit?
Oh, it's been wonderful. Yeah, it's been really good. Making a lot of new friends, and it's nice to be so in the winter on a nice day. Thank you. Thank you so much, Alan, for that warm introduction. It's really a pleasure and delight to be in Seattle on such a beautiful day. Someone tried to convince me that it's always like this. Didn't completely buy it, but I'm willing to believe it today. So it's really particularly special to be here as the student seminar speaker. It's someone who really enjoys interacting with students and mentoring students. It means a lot to me to have an opportunity to not only visit the department, but also to have a day where I spend time with students, meals with students, and it's been incredibly fun, and look forward to tomorrow as well. For today, I wanted to describe some work that I've been doing with some colleagues. My student, Elsa Yang, Yahong Yang, and Arun Kubichatera, who is at CMU. And the goal of today is to describe what we've called the Forster-Warmuth nonparametric counterfactual regression. So that's a mouthful. And there are various parts here. So the way I've organized the talk, oops, what do I want to do? Okay. And if I want to go back? Okay, sure. Okay, thank you. So just a quick outline of today's talk. So if you're not familiar with nonparametric regression, if you're not familiar with counterfactuals, if you're not familiar with any of the words in that title, do not be concerned. We're going to build it up slowly. And hopefully I will convince you by the end of the talk that this is an interesting method that you might consider using if you have a problem for which it's appropriate. So I'll first describe a long existing literature in statistics on series regression for nonparametric estimation. Nonparametric regression is one of the most foundational problems in statistics, and there's a long history of it. So I won't be able to cover the whole history, but I'll pinpoint certain aspects of that history that will be relevant for the rest of the talk. Then I'll describe a new estimator that we developed, and just to honor Forster-Warmuth, because we named it after them, to continue in the mesonomy tradition of statistics, because we actually do believe that this idea was introduced by them in a completely different setting, in an online setting. And we only just noticed that this could be a useful tool for nonparametric regression. They were actually using working linear models, but they had this amazing result that blew our minds, and we realized that the contribution maybe was to point out that it's a useful tool for regression, nonparametric regression analysis. So that would be the first part of the talk. The second part of the talk is going to be about what we call counterfactual regression. This is also a very old problem in statistics, in causal inference. This is an issue of when your outcome is not observed on every subject, is missing for some subjects, and you have some assumption that allows you to account for the missingness. And the question is, how do I do nonparametric regression in that context? And we'll use the Forster-Warmuth estimator to then combine with the counterfactual regression ideas to try to address interesting and problems that we think are important in public health and other kind of applied work. All right, and then I'll maybe talk briefly about simulations and application, illustrating the utility of the methods in a specific context, and close with some remarks. Now, nonparametric regression plays a central role in statistics, and I would argue more broadly in scientific inquiry, where one is interested in describing a conditional mean regression function that looks like the mean of y given x, where x might have some discrete or continuous components. Today, I'm going to focus on x having continuous components only. And one who is, the foundational question here is, how do we learn about this kind of regression function without a priori restricting the model? So without necessarily assuming that the model follows a particular functional form, we want to be flexible. We cannot be too flexible, otherwise we don't learn anything. And so how do we encode information that we might have and that we trust might be reasonable? How do we adapt to the data. These are all important questions. I'll only touch on some of them today. So an example of conditional mean function would be, for instance, if you were interested in a conditional cumulative distribution of an outcome y at different values t. Given x, and you want to describe the functional form of that as flexibly as possible. And this is also particularly important in the context of finding quantiles of a distribution. When the mean is not enough to describe what might be going on, and you want to describe what might be going on at different quantiles of the outcome. In fact, this is a very generic problem and general problem in the sense that you could also think of it as being a tool for estimating any conditional function defined via an objective function as described here. So you have a loss function rho, and you want to find the function theta that minimizes that conditional mean of that loss function given x, and the solution will be a function theta star x. There are several problems that fall in this category, like the so-called nonparametric instrumental variable problem in econometrics would be one of them. Proximal causal inference might be another one, and many more. So the goal is clear. We want to describe a conditional mean of y given x. And the most intuitive method, and probably the oldest method, don't quote me on that, but I think it's been around for a while, is so-called series or sieve estimation, which basically approximates the unknown conditional mean function by combining, by taking a linear combination of k basis functions. Could be polynomials, could be wavelets, could be Fourier series, just some kind of basis function. And I'll go over a couple of them a little later. And you truncate the series at some point, and you in this case, I'm truncating at k. So if they're polynomials, I take polynomials. So the components phi1 would be 1, phi2 would be x, phi3 would be x squared, and so on. And then you truncate it at x to the k minus 1 power. And so you have k basis function. You take the linear combination, and you take that as a representation of the mean of y given x in the case where x is scalar. If it's multivariate, you take the tensor product, and you can create multivariate basis functions that way. Okay, and so very simple idea. Looks like a regional regression, except we're not regressing on x directly. We're regressing on some fancy functions of x. Why fancy function of x? Because we want it to be flexible. And so there are going to be some approximation properties of the basis function that are going to play an important role later on. But one aspect of this is a little deceptive, which is that it looks like a linear regression, but it's not a linear regression in the usual sense, because we want k, in fact, to depend on sample size. We want the level of approximation that we can attain to be pegged to the sample size. The more data, the better the approximation. So the larger k we could potentially afford to do, the smaller sample size, the lower the approximation we can afford to do given the data at hand. And so the deception here is that, in fact, even though it might look like a standard regression analysis, it's a regression analysis with potentially, in fact, the number of covariates growing with sample size in order to attain estimation of the conditional mean of y given x. That is a flexible estimation in some precise sense, in the sense that we ultimately want to balance bias and variance, the very old trade-off in statistics. In this case, the smaller the k, the larger the bias, the smaller the variance. The larger the k, the smaller the bias, the larger the variance. And that is the trade-off. And so ultimately, we want to pick k, the number of terms, to be minimax in some sense. Okay? And there is a literature on this. One of the oldest and most straightforward empirical approach to construct a series estimator is least squares. You simply take your basis functions. Here's some notation for it. So I'm only going to talk about the IID setting today. So we have covariate X, multivariate, all continuous, and outcome Y. And we aim to estimate M star of X, conditional mean of Y given X. And the simplest possible estimator would be to do least squares on the basis function. So here is a least squares estimator. And I've now turned phi into a matrix phi. So phi to include the empirical evaluation of the least squares estimator. So each component of so phi bar k here is the vector of all the basis function evaluated at the first data point x1 through xn. And then you just apply your standard least squares formula, okay? And please interrupt if anything isn't clear. And you get a linear combination. So looks like stat 101, just doing linear regression on the basis function. And in fact, this type of estimator has been around for a while and has been extensively studied in the literature, both in statistics, but also very much in econometrics. There are several papers that provide sufficient conditions for consistency, the convergence rates, depending on how K is allowed to depend on N, and even asymptotic normality of the estimator in very pretty mundane cases such as polynomial series, but also fancier one like regression splines, Fourier series, wavelets, local polynomial partition series. And there are too many to cite, and I mentioned some recent and some older literature on this. Okay. Now, let me maybe say a little bit about the theoretical properties that was derived for these types of estimators in the literature and why are they important. So these prior works established that under certain conditions on the basis function, which I'll provide in a couple of slides, which has to do with the ability to approximate any arbitrary function well. And assuming that M star lives in a Holder space, and a Holder space, the way I want you to think about it is that it's basically a smoothness class. The more derivative the function has, the smoother it is, right? A line has infinite number of bounded derivatives. And then some constant Cm for the radius of the ball. But just think of in terms of derivatives. The more derivative, the more I'm willing to assume the function is smooth. So beta M is that number. And so what's been shown is that if in fact you set the number of terms in your basis series estimator to be equal to n to the d over 2 beta m plus d, where d is a dimension of x. Okay, if you choose that, then the mean squared error, defined here, square root of the mean squared error, is of order given by this formula. Now, two things to notice here is the reason this is not like standard linear regression is because this is going to converge at rates much slower than 1 over n, or 1 over square root of n in this case. Why is that? Because in fact, you could see that for any beta that's bounded, any constant beta, this rate is going to be bounded above by 1 over square root of n. The larger beta m is, the faster this rate is to converge to 0. In fact, if I let beta m to go to infinity, this converges to n to minus a half. The larger the dimension d, the slower this rate is. The smaller dimension, the faster this rate is. Curse of dimensionality. So everything makes sense. Okay? And this actually describes precisely the minimax rate of estimation. There is no estimator without making an additional assumption that has a faster rate of convergence. And these papers establish this result that the least squares estimator is minimax optimal. It's a pretty damn good estimator for smooth functions. Very simple, nothing fancy. Just do least squares on your basis function, pick the basis function theoretically according to this rate, but you can do other things. You can do squash validation. You can do it. There are other ways of finding the optimal rate of estimation. And if you don't know what beta m is, that's the point. You want to be able to adapt to beta m, but I won't talk much about it today, but there are tools out there to do so. What these papers have established is that least squares on these basis function is in fact rate optimal in probability. So it attains this minimax rate. Can't do better without an additional assumption. Specifically, this is known to hold for local basis functions, including Fourier, wavelets, splines, local polynomial partition series, for all combinations of beta m and d. Nothing can do better in probability. In contrast, for the more mundane basis function, probably the most intuitive one, polynomial series, it turns out that it's only minimax provided the number of derivatives is greater than the dimension of x divided by 2. So in one dimension, this is basically saying that you have to be smoother than an object that has a half derivative. If you don't know what that looks like, you're in good company. Most people don't know what a function of half derivative looks like, but you can think of Brownian motion. Okay, that would be such an object. It's very rough. And this scales with D. So for any D, as long as you go below D over 2, polynomial series stops being rate optimal. You have to use something else. Okay, so we were puzzled by this result. Okay, and for reasons that I'm going to explain in a few slides. The one aspect of this result I puzzled out is that if you actually spend time looking at the proofs of these results, they very much critically rely on the size of the basis function, as well as its ability to approximate smooth functions. The second one makes sense to us. If I have a basis function that's a good approximator of smooth function, and I just do least squares, in principle, I would think that it would do well. But it turns out that actually, all of these proofs relied on actually very careful calculation to characterize the role of the size of the basis function. And that turns out to play a role in their proofs. Specifically, this optimality result of least squares requires that the size of the basis function, so this is the Euclidean norm of the k vector, and then you soup over the support of x, this can grow no faster than square root of k. And then that result holds. In addition to that, so this is the size, the constraint on the size of the estimator, and this turns out to break down with polynomial regression as soon as the number of derivative is less than half the dimension of x. Okay. In addition to this assumption, to controlling the size of the basis function, it turns out that your basis function must also have a good approximation property. Now, I want to say something because this sounds like a theoretical talk, but this actually matters for practice. The reason asymptotics is needed is to understand if I want to solve a real problem, I want to get a function describing the risk for COVID according to factors such as age, how much you smoke, factors that are continuous. And I want to do it non-parametrically because I want it to be credible. I want to be flexible. Then it turns out these asymptotic results are good guidance for what you should do in practice because they inform you on what you should expect in finite sample. Okay? And so that's kind of why we engage in this exercise. And I'll try to show the difference in simulation and application a little later, but bear with me for now. I want to motivate the theoretical with the theory. And so the second part makes sense. This doesn't include any notion of size. This is about the ability of the function, of the linear combination of basis function to approximate the underlying function m star. So m star is the mean of y given x. And if I truncate my basis functions at level k, then the bias, right, the tail behavior of that function, the bias, the difference between my linear combination and m star, there must exist some beta such that that beta is the approximation error is bounded out above by k to the minus 2 beta m over d. Where again, beta m is how smooth the function is. So the larger beta m, the faster that rate converges, the easier it is to approximate the function. Example, a linear function. I only need a line with k equals 2, and I have no approximation error. Okay. And then d being the dimension, and the larger d again, the worse the approximation. Again, the curse of dimensionality. Very hard to approximate things in high dimensional space. Okay. All right. So it turns out this result is actually known for all the basis functions I've mentioned. They all satisfy this approximation result. But the size of the basis function only satisfied by some, but not all. Okay. So what am I going to describe in the rest of the time? So we've developed a new type of series regression, which is incredibly intuitive. And my test, I think I mentioned this to Ellen, that we're meeting tomorrow, and Ellen said that reading the abstract, it was incomprehensible. And the test is going to be whether tomorrow you can tell me whether or not it made sense. No pressure. Okay, so we've developed a new type of series estimator, which I'm going to describe. And it's just a small adjustment of the series estimator that attains well-established minimax non-parametric rates of estimation in settings where covariates and outcomes are fully observed under weaker conditions compared to the existing literature. As I mentioned earlier in the introduction, that the approach is based on this work by Forster and Warmuth, and thus we name it after them in the online literature. What's the estimator? Okay, so here's the estimator. I have a lot of terms in here, but I want to point out something. Suppose A were 1, suppose B was 0, and suppose C didn't have this phi term and the 0 term, then you will be back to the least squares estimator. So we made 3 modifications to the least squares estimator. You can think of this as localization. Suppose I want to predict M at little x. Okay, so let's talk about A. A is equal to 1 minus Hn. Well, Hn, if you recall from linear algebra, Hn is actually the leverage for the covariate space spanned by phi. So what's the leverage measures how far from the distribution of the covariate is a particular observation. It's a measure of outliers in the X space. So what H is doing, H of n is saying, first, we're going to do leverage at little x, and then we're going to add a fake observation at little x. Because x is continuous, probability 1, I'm not going to observe any data at little x I'm interested in. So first, you add a fake observation there. You compute the leverage. Okay? Then the leverage is known to lie between 0 and 1. What is this property? If you have very high leverage, then Hn is close to 1. And this is going to penalize it and shrink it all to 0. So what that means is that if I have a big value, the basis function at some particular x wants to be an outlier, I'm going to discount it incredibly. I'm just going to shrink it to 0. So that I say, no, the size shouldn't matter. They're putting it out of control. Okay. Because I'm doing that here, I'm adding this observation x. I'm also going to add it in the design matrix. So imagine little x were actually my sample, then this matrix would be just the regular matrix x transpose inverse. Okay. So B and C incorporates a fake observation at x to the design matrix with corresponding y equal to 0. While A adjusts for the leverage of this observation if extreme relative to observed basis functions. This effectively controls the size of the projection matrix at the specific value of x, regardless of the basis function. This does away with having to control the size of the basis function. You can construct this estimator with any basis function. All you require is the basic function has a good approximation property, which is known to hold for most of the ones that I mentioned here at least. So we have our first result that says, suppose that the conditional second moment of y is bounded, almost surely, and the basis function phi satisfies the optimal approximation property, which is a good approximator. Then there will exist a beta such that, and this is the approximation property that we require, and this is satisfied by all the basis function I mentioned. And we would just pick the optimal k that I mentioned earlier. And what we're able to establish is that the Forster-Warmuth estimator, under these conditions, regardless of the size of the basis function, is going to be minimax. And this is a stronger result than the previous one because this is actually mean squared error, supposed to be in probability. And so this tiny change of just controlling, and it sounds a little weird because we're really changing the estimator, and it sounds like we should be introducing bias. Because whenever x wants to escape, we set it to 0, but we're looking at mean squared error. So those values on average don't contribute anything once I take the average over all x's. They can be completely ignored. And so this particular construction is the Forster-Warmuth construction. It robustifies the least squares estimator in a manner that establishes that as long as your basis function is a good approximator, you're guaranteed to get the minimax rate. No estimator can do better in terms of mean squared error for smooth functions within the Holder ball. So that's the first part of the talk about just plain old nonparametric regression in statistics. So the Forster-Warmuth estimator is minimax rate optimal with respect to the mean squared error for any basis system that constitutes a full approximation set in the sense of Lawrence and Yang and Barron. including polynomial basis for all combination of beta M and D. The first part. As I mentioned, the corrections A through C rather, in the Forster-Warmuth learner are key to this result and obviate the need to control the size of the basis function. Note also that A through C become negligible in large samples, and that the Forster-Warmuth in large samples basically behaves like the least squares estimator. So what the implication of that is that there are a lot of really good asymptotic results for the behavioral least squares estimator in non-parametric settings, particularly asymptotic normality, constructional confidence intervals. All of those can be used in this setting. Okay, so we inherit that rich literature or inference for non-parametric objects. We also established that the Forster-Warmuth learner itself is bounded. Now, this is an important property. You may be familiar with some work in cross-validation. So Joffe in 2002, in their book, they have some theory for that, but also Van der Vaart, Gidois and Van der Laan have a really beautiful paper, elegant paper, where they demonstrate that cross-validation works. That if you do cross-validation on a class of estimators, it's going to find the oracle one, the best one. Okay? And one requirement in that theory is that the estimator needs to be bounded. It's not easy to get a bounded estimator. By using that leverage quantity, it ensures that the estimator is bounded. So that theory is inherited. You can do oracle selection using cross-validation. And this goes to whether or not you know beta M, how smooth the function is. So you can adapt. If you don't know what it is, use cross-validation with the Forster-Warmuth estimator. And you'll, according to their results, you can find the optimal estimator that way. You can adapt to beta. Any questions? Yes.
Is there a consistent centering when I think about shooting for 0, is there something special about 0, or is it sort of like a without loss generality?
There's nothing special about 0. You can shrink it wherever. The point is that this is a rare event to your average. Okay. All right, so let me start with the second part of the talk. There are no other questions for the first part, and then we'll combine the two ideas. So the second part of the talk is about non-parametric counterfactual regression, and for me, this was the real motivation for this work, because I actually have application. I'm going to try to describe some of them, where counterfactual regression is important. So in many practical applications in health and social sciences, it is not unusual for an outcome to be missing on some subjects, either by design, say in a two-stage sampling study, where the outcome can safely be assumed to be missing at random with known non-response mechanism. Two-stage sampling, two-phase sampling, actually, a lot of it was developed here by Breslow and some of the area by John Wellner as well. And so this is a strong motivation. This, I feel, is a good home for some of these results. And or the missing data could be by happenstance, in which case the outcome might be missing, not at random. So I'll give you two examples that in the literature. One is mine and the other one is not mine. So this one is not ours, but it was a colleague at the Harvard School of Public Health, where they were interested in building a polygenic risk prediction model for type 2 diabetes based on, and what they did, based on a stage 1 fully observed covariate data on participants, including high dimensional genotype. So they have the genotype for everyone, they have age and gender for everyone, and they want to predict diabetes. And it's expensive to get a panel of physicians to come and get consensus on a diagnosis of diabetes. So they designed a two-phase study where the second phase, they take a subsample of the underlying cohort, and then they convene however physicians they can afford to convene to go over charts. Very costly and time exhaustive process. And then they get the outcome on that subset. And now they want to get a polygenic risk score for prediction in the population. They want to do it non-parametrically. Okay? So this is an example of missing outcome, but it's missing by design. So you know the missingness process, control it. And it's important to control it in a manner that it depends on the covariate, because you want it to particularly in areas where you believe it's going to be harder to get good prediction, you want to oversample those parts of the distribution. The second example is actually an example in a study of ours in Zambia. It was a household survey in Zambia for HIV. And this was nested within a regular household survey where we go and visit the household. We ask a number of questions related to health and welfare in the household, on all members of the household. And at the end of the visit, we asked participants if they were willing to test for HIV. Okay. Nearly 30% declined to test. That's a lot of missing data for something as sensitive as HIV status. The concern here might be that participants who decline to test might not be a priori exchangeable with participants who will agree to test for HIV with respect to key risk factors for HIV infection, even after adjusting for fully observed individual and household characteristics collected in the household survey. In other words, we don't believe this is missing at random, and certainly not completely at random. Any effort to build an HIV risk regression model that generalizes to the wider population of Zambia requires carefully accounting for HIV status, possibly missing not at random, for a non-negligible fraction of the sample. Okay, so this is a setting where it was clear to us that it was completely unreasonable to assume missing at random. So I'm not going to spend a lot of time on this, but the point I'm making here is that the kind of assumption you'll need for identification is kind of orthogonal to the learn that I'm going to describe. Okay, so for identification, the first part, it was straightforward. We control the missingness at random. And so we can use IPW, augmented IPW kind of construction. And I'll describe that in some detail. In this second example, it's missing not at random. So you might ask, how are we going to deal with it? The way we dealt with it was actually using an instrumental variable technique. Now, you may or may not have heard about instrumental variable. If you're a causal inference person, you would have heard of instrumental variable in the causal context. If you're an economist, you would also be aware of instrumental variables in the missing data process. In fact, there's a method known as the Heckman selection method, and he got a Nobel Prize for it, and it was to deal with missing data. So there's this whole literature on IB for missing data, and the one that we use here is actually a really simple design-based IV that's very credible. What we did is we used interviewer characteristics, the people we sent to the household to interview people. In this context in Zambia, it turns out if you're an old man and you have a young woman come to your household asking you to test for HIV, it actually makes a difference whether or not you agree. And you can see that in the data. You can see the non-response rate varying with the interviewer characteristics. However, your interviewer characteristic cannot impact your HIV status. That's an exclusion restriction. So you can actually use instrumental variable methods to account for missingness not at random based on that observation. And there are very good choices of IVs in that context. And they actually tend to be a lot stronger IVs than in a causal inference context. So if you're a causal inference person and you have a rich set of methods that you've explored in causal inference using IV, know that there's a parallel world in missing data. And you don't have to acknowledge me, but you have a rich literature in missing data that you can actually now start writing papers about, because there's a mapping for every method in causal inference to a missing data problem. Okay, so just to say that identification in this context is actually very doable and very credible. Beyond missing data, counterfactual regression can also arise in causal inference, where one might be interested in the conditional average treatment effect, that is the average causal effect experienced by a subset of the population, defined in terms of measured covariance. Missing data in this case arises as the causal effect defined at the individual level as the difference between the two potential outcomes, one for each treatment value, can never be observed. You only observe one of them. This is because under consistency assumption of causal inference, the observed outcome for subjects who actually receive treatment matches their potential outcome on the treatment, and likewise for the untreated. So what we've done in this paper is to propose a generic construction of what we refer to as a pseudo outcome which, as its name suggests, replaces the unobserved outcome with a carefully constructed response variable that satisfies two conditions. One, it has to be a function of the observed data. You have to be able to evaluate it. And so it only depends on the observed data, possibly involving some nuisance functions that can nonetheless be identified from the data. So everything has to be identified from data that goes into constructing the pseudo outcome. And two, this is an important property. If I take that pseudo outcome and I've constructed it for everyone, including those who are missing the outcome, it must have conditional expectation given covariate that matches the counterfactual regression of interest. Okay. If, as for an oracle, the nuisance function were known. So it has to be something you compute, and it has to be unbiased, conditional on the covariance. And we're then going to use this pseudo outcome as the outcome in our nonparametric regression. In particular, we're going to use it in the Forster-Warmuth regression. That's the idea. So the proposed pseudo outcome approach applies to a large class of counterfactual regression problems, including the missing data and the causal inference problems described above. In many cases, it actually recovers estimators that have been proposed in the literature, and so this could be seen as a generalization of those estimators. And the part I'm particularly excited about is that it actually provides a readily easy solution to many problems that haven't been considered in the literature. Non-parametric quantile causal effects, for instance. That was one that has received little attention in the literature. And this particular construction readily generalizes to scales that are nonlinear as opposed to the conditional average treatment effect that's additive. Nevertheless, I'm going to focus just for the sake of presentation on this traditional, just to explain how it works with the traditional conditional average treatment effect on the unconfoundedness. And so this is how it's typically written. Is the condition consider a strata of the data, X, and you're going to look at the causal effect for individuals who fall in that stratum. And that is contrasting the outcome for a given individual if they were treated to the outcome if they were not treated. On our confoundedness assumption, we're assuming that condition on the covariates, there's no confounding. So this would be identified by the observed data, but just the difference of the regressions between the treated and non-treated. You may have philosophical differences as to what assumption is being used. The point that I really want to emphasize is whatever assumption you're going to use for identification is tangential to this procedure. For any given identifying strategy, there will be a corresponding pseudo outcome. So you can think of this as a meta algorithm that you can wrap around any kind of identification criteria. So if you're uncomfortable with unconfoundedness, you need not worry. Whatever you're comfortable with, you can assess it. You can use it, rather. So we assume consistency and positivity throughout, which basically essentially means that the first one is, let me spend a second on this. For those of you who might not be familiar with this. So this is almost, sounds like a tautology, but it's actually an assumption that the observed outcome would match the potential outcome for the treatment actually you receive. If you're treated, it matches the outcome on the treatment. If you are not treated, it matches the outcome on the no treatment. This presumes that there is a single version of treatment and we agree on it, and all other versions are irrelevant. It also presumes that there is no interference, which means no network interactions. Okay, so this would be an issue, for instance, in herd immunity settings for infectious diseases, but we have ways of relaxing that. Betts has done a lot of work in interference, one of the first people to have written on the topic. And so there are ways, arguably much more complicated by ways of relaxing these assumptions, but this is probably 99% of the literature in causal inference relies on this assumption and considers it to be reasonable. In many settings. Okay. So in this particular instance, M star X is you see it's a regression function, but it's a counterfactual regression function because we don't observe YA1 and Y equals 0 for everyone. We only observe one of them. So if you're treated, we observe this one. If you're not treated, we observe that one. And we want a regression of the difference of the two. Okay. So that's the missing data part of it. What's the role of the Kate? Well, one important role, at least of late, is that it plays a central, it's central to precision medicine, as not only does it quantify effect heterogeneity to the extent that to which X predicts a person's causal effect, it also can be used to decide whether or not a patient should be treated by looking at the sign of M star. For depending on Y, larger values of Y being desirable, then you look for positive M stars. So our starting point is to ask, what would an oracle with access to the both counterfactual do? Well, in principle, if you have access to both counterfactuals, you would just take the two and then run a Forster-Warmuth regression. And you would automatically get the guarantee from the non-parametric minimax result that we have for the Forster-Warmuth. Combine that with cross-validation, you can get adaptivity. So that's not as interesting. Second question would be to say, well, I'm not an oracle, but I can run a randomized trial, in which case A is randomized, Bernoulli a half. What can I then do? I still don't observe both counterfactual. I get one of them, but this is, I get a representative sample of each counterfactual. And so what I could then do is I could just construct a statistics, a pseudo outcome H, which just takes the outcome, the observed outcome, and weights it by this quantity. And all this quantity is doing is the two is just 1 over, it's inverse probability weighting. So it's 1 over 1/2, that's the 2. And then this term, all it does is, because A is Bernoulli a half, when you average over it, it creates this difference between the outcome Y's, okay? And this is a pseudo outcome. So you would take that pseudo outcome and you would regress it on X and you're done. Use the Forster-Warmuth regression. So you could use this in a randomized context if you want to do prediction of the K. And what the conclusion is would be again that you would inherit all the properties of the guarantees that come with the regression method. Neither approach is feasible in observational settings when A is not randomized. Therefore, the most we can hope for is to construct an H hat. We're going to have to estimate H because we don't have a randomized experiment. I'm going to focus on settings where we assume unconfoundedness. And so we have to somehow incorporate the covariates X to adjust for the confounding. And that will lead us to having to estimate certain nuisance functions. And that will lead us to an H hat. And the question here is, what are good H hats? How do I obtain an H hat that's good? Because now I have to incur a cost for having to estimate the pseudo function, the pseudo outcome. And so we refer to this as an H that has small bias. How do we construct an H that has small bias? That's the second contribution of the paper, and hopefully I'll get to it in a few minutes. My goal was to end in 50 minutes, but I'm going to discount the 10 minutes you took to introduce me. But I'm not going to, I shouldn't be too much longer. So how do we construct a pseudo outcome in the causal context? It's going to require some identification condition. As I mentioned, we assume no unmeasured confounding in this case. And in such case, it's known that there are at least 3 constructions that are very well established. So I'm going to go through them. The first one is essentially an observational version of the one that I mentioned in the randomized trial. The only difference is instead of having a half, now I have to incorporate a propensity score for the treatment that you receive, standard inverse probability weighting. So that's one of them. And you just estimate it, and that the hat under the propensity score is what makes H hat. Okay. And you can use a nonparametric estimator for the propensity score and incorporate it in this case. The second one is so-called G computation or outcome regression. And it entails running the regression in each arm and then taking your difference, given X. Excuse me. Where the regression on each arm is, again, using a non-parametric estimator of your choice. Unfortunately, these natural choices do not lead to small bias. And that's because the bias is going to be dominated by either the bias of your regression, if you use this technique, or the bias of your propensity score if you use this technique. And it's possible, as we'll argue now, to get smaller bias, in which case we'll describe these methods as not having small bias. All right, so there's a lot of stuff in there. I'm gonna walk you through it. I know you were like, okay, we're almost done with the slide. There's not gonna be any more theory, but this is actually the one result that we're particularly excited about. And so I wanna share this with you. Okay, so I'm gonna go through every line. So bear with me. So M star is a counterfactual quantity we care about. Think of the Kate. Okay, so that's counterfactual. It's expressed in terms of latent variables that you don't always observe. We have some assumption that links it to the observed data. Okay, and let n star of x be the observed data function that identifies the counterfactual M star. So on unconfoundedness, eta star of x will be the difference in the mean of y given a and x across levels of A, the treated versus the control. That's one particular formula that identifies an unconfoundedness. If I'm willing to make a different assumption, for instance, if I have an IV, then I'll have something like a wild statistic as the identifying function. The point is that it's going to be some regression function. It can be a really complicated, it can be a ratio of regression function, whatever it is, call it n star, and it's going to invariably depend on a nuisance function, which I'm going to use eta generically to denote all nuisance functions. Okay. And suppose that I hand over to you a pseudo outcome R of eta that satisfies, if I take its mean given x, under my identifying assumption, I recover the Kate. So three things to keep in your mind. M star is the underlying thing I care about. It's not necessarily identified. I have to identify from the data under some assumption. When I identify from the data, I get an n star. In addition to the n star, I hand to you a pseudo outcome R. So go back to the Kate example. The pseudo outcome R could be H that I constructed under those two scenarios, either H from IPW, and therefore eta in that case is the propensity score, or H from the difference in regression, in which case the two regressions are eta. Okay, so those are R. In some instances, R matches n star, like with the difference in two regressions. In some instances, R is a random object, like in IPW, right? It's -1 to the 1 minus A over the propensity score times Y. Okay, so those three objects in your mind. Okay. All right, I can do this. So I hand you over an initial pseudo outcome, and I'm not happy with it because it has at least too big of a bias. I want something that has a smaller bias. So the following result gives you a sufficient condition to be able to construct that object, and also gives you an explicit way of constructing it. All right. So sorry. Okay, so suppose that there exists a random variable R in L2 such that for any regular parametric submodel of M is your identifying model. We have that if I were to perturb your pseudo outcome in the direction of your nuisance function, and I take the derivative in that direction, I can find an object, capital R, a random variable, that whose inner product with S, conditional X, matches that derivative. Okay, this is a mouthful. This theorem is essentially just telling you that derivatives can be written as linear operators. And there are many examples, and I'll give you some examples where we can characterize R. The key here is that for a given initial estimator, you need to solve this integral equation to find R. Once you find R, you can combine R with your initial estimator. And if you look at the bias of combining R with your initial estimator versus the true parameter of interest, so this is a bias. This one is evaluated at eta prime, and one is evaluated at the true eta. That bias is going to be guaranteed to be second order. This is very similar to what's been known as, my goodness, what does he call it? Neyman orthogonality in econometrics. These are statistical objects that are constructed to deal with nuisance functions so that you're guaranteed to get second order bias, quote unquote small bias. What do these construction look like? And I'll give you some example in the next few slides of how to solve these equations. And the point of this theorem is essentially to offer a sufficient condition to be able to bias correct R. I should point something out. Some of you may be familiar with semi-parametric theory and pathwise differentiability. This is not pathwise differentiability. because these are not pathwise differentiable objects, but it's very similar. It plays the same role. So this theorem formally establishes that the pseudo outcome for a given counterfactual regression can be obtained by effectively deriving an influence function for a marginal object. Let me just skip ahead of this. It's not that important. All right, so as I mentioned, this is going to be useful for a comprehensive class of counterfactual regression problems. And I also mentioned that it's a version of what's been known as Neyman orthogonality. This is a second order property of the bias. So an implication of this result is that whenever the second order bias of your pseudo outcome is bounded above by the oracle rate of the Kate estimator, you never pay a price for having to estimate the pseudo outcome. You will pay a price if it's larger, and the price you'll pay will be exactly the size of this bias. The implication of this result is that in practice, you're going to construct estimators for eta that are as adaptively as possible, okay, as adaptive as possible to the data. One important question is, when does this happen? When can I characterize when this occurs? This turns out to be a pretty difficult problem to solve. There's one paper on this topic by Jamie Robbins and Rajashi Mukherjee and their colleague Lin Yu in Journal of Econometrics, I think. But it's barely scratching the surface. This is a really important problem in the sense that we want to diagnose when our estimators actually behave the way we want them to behave. All right, let me go back to the Kate example. What does this look like in the Kate example? So in the Kate example, if you were to take the difference in mean as your initial pseudo outcome, and you solve that equation, so the pseudo outcome is R, little r, and then the capital R will be the correction term. It turns out to just give you something that looks exactly like augmented inverse probability weighting. So it's nothing surprising in this case. It recovers something that's already been known in the literature. The corresponding empirical pseudo outcome would then plug in estimates of all the nuisance function. And then you will take H hat and you will plug it into the Forster-Warmuth learner. And the bias of the Forster-Warmuth learner would be second order, and in fact, the product bias structure of the two nuisance function. So if these two functions are not particularly smooth relative to the Kate, however, the product happens to be a smaller order than the Kate, you can effectively ignore having estimated these two nuisance functions. If it's larger, you cannot ignore it, and this will be your rate of convergence. Now, note that the above results continue to apply if, as often the case, we aim to evaluate the Kate with respect to a subset of the covariates. So I have X, a large set of covariates that I need to adjust for confounding, but I only care about the Kate with respect to one covariate. And that's actually going to be the case in my application in a few slides. Okay. And so this is what I care about. V is one covariate in X. So all you do is you do exactly the same construction. You construct your H, and then you regress it on basis function that only depend on covariate V. The natural thing to do. And you will inherit the rate for the Kate in one-dimensional Kate, which is arguably a better rate. Actually, so we have some simulation results that I wanted to share with you. Let me maybe focus in the interest of time just on this one. So this is just comparing the behavior of 6 estimators. What I've done here is I have solid lines and dashed line. The colors are representing whether we're using the Forster-Warmuth estimator. So the dashed line is just using least squares, and the solid lines is using the Forster-Warmuth estimator, the same basis system. And we have different basis system. We have B-splines, we have polynomials, and then we have I forget what NS is. It's some kind of spline. That's that I remember. It's a different. I think it's regression splines. I don't know why we have N there. Is that R? Okay. And what we've done here is we're looking at it over a range of how well you estimate the propensity score. So moving from the left to the right, for two different sample sizes, 2,000 and 400. Moving from the left to the right is how large alpha is. And alpha determines is essentially how smooth the propensity score is. And so this is giving a sense of the difficulty of estimation of the nuisance function. Now, the bottom line in this simulation is looking at the ratio of mean squared error comparing to the Forster-Warmuth, is that the dotted line is always sitting above the solid line. The dotted line is the least squares estimator. The solid line is the Forster-Warmuth estimator using the same basis function as the least squares estimator. Under challenging situations where you have outliers in the covariate space. And so the behavior of the least squares estimator becomes very unstable because the size of the basis function drives it. And the Forster-Warmuth corrects for it, leading to a reduction in mean squared error. Okay, so the last couple of minutes, I'm going to go over an application of the method and then close with some concluding remarks. In this analysis, we revisited a well-known study known as a support study, which the aim of evaluating the causal effect of right heart catheterization. This was an observational study published back in 1992 by Connors in JAMA. And this is looking at the impact of right heart catheterization during the initial care of critically ill patients in the intensive care unit on survival time up to 30 days. RSC was performed in a little over 2,000 patients within the initial 24 hours of ICU stay, while a little over 3,500 patients were managed without RSC. The study collected rich patient information. There are 73 covariates in total. The outcome of interest is the number of days between admissions and death or censoring at 30 days. Okay, and these are the covariates that were collected. If you want to have an idea, we're going to be interested in the Kate with respect to the baseline estimate of the probability of survival, because that's a very quantity that's meant to not only is it a strong confounding factor, but it's a strong prognosis factor that physicians use. And understanding how the causal effect of the procedure varies with this initial score of a prognosis score is incredibly important. Now, this data set has been analyzed a lot in causal inference papers, and primarily looking at the average causal effect. The idea of looking at Kate, and one of the surprising things about this analysis is people initially, I think, expected it to be RC to be protective, and it was found to be harmful overall to the population. And I had is anyone here a cardiologist? I had a cardiologist once when I gave this talk, and I got a whole lecture afterwards because the way I was describing it was a surprising result. And he said, yeah, everyone actually hated RHC. They wanted to get rid of it. So it was actually a welcome result, right? And then, so make sure to always state that. That is not as commonly practiced these days, apparently. So what we did here is we wanted to describe how this causal effect changes with your risk of survival, a heterogeneous causal effect. So what I've done here is I've done something that's maybe unfair to you all, because I suddenly introduced a new method in my application, which is proximal. This is what I discussed, unconfoundedness. So unconfoundedness is assuming that there is no unmeasured confounding, the method I described, and then we estimate the Kate as a function of your probability of survival, and you get these subtle results, more nuanced result that in fact, individuals with a lower probability of survival actually benefit from it because that survival positive is good. But individuals with a higher probability of survival actually were harmed by the procedure. And so this is why the Kate is important, because it gives you more nuanced information about what might be going on. Proximal causal inference is still using the same Forster-Warmuth estimator, but it's using a different identifying condition. So the pseudo outcome looks completely different. And what proximal causal inference does in this case is allowing for unmeasured confounding, provided I can treat my covariates as proxies of the unmeasured confounding. Okay. And it tries to account for it. And what we get by that is essentially we get an attenuation of the causal effect, and we only have evidence of a harmful effect for individuals with higher values of baseline probability of survival. And so hopefully this at least conveys this idea that this is actually useful tools to do. The only reason we can interpret these findings is how precise these curves are estimated, and the ability of them being estimated precisely relies on these minimax theorems. So that those formal results in turn translate into meaningful applied interpretation of the application of the methods. Okay. A little over, so let me conclude. I wanted to briefly mention some other counterfactual regression problems and their pseudo outcomes, because I found that intriguing to come up with. So here is a conditional quantile treatment effect. So let's suppose Q were a half. So F is the CDF of Y. So that's the quantile. So if Q is a half, then we're picking the conditional median for Y for the treated and compare it to the control. This should be A equals 0. Sorry about that. Okay. So this is a hit on a completely nonlinear scale. It's no longer the average treatment effect. It's a quantile, the difference in quantiles, conditional X. And want to describe heterogeneity with respect to X then. So that's the quantity of interest. So this can also will be identified from the data by just the difference in quantiles. So this could be your initial pseudo outcome. You use our theorem to derive the correction, and that's the correction that ensures that your pseudo outcome has second order bias. Okay. And so that's one implication of the result. What's interesting about this is that the initial estimator is quite simple. Unlike the other estimators that I described, this is actually a really nasty one to implement because it's going to involve, and this shouldn't be surprising, it's going to involve the density of the outcome evaluated at the median, in this case, the quantile Q. Okay, so it's the density at a point, conditional ANX. And so numerically, the pseudo outcome is one thing, but the implementation of it is going to matter because we're dividing by this density at a point. That can be a problem. So we see this more as a starting point for exploring these other questions. So here's another one. So we did the conditional average treatment effect on the additive scale. Well, you might have a binary outcome and you might care about conditional average treatment effect or a count outcome. So you want to apply a link function. So suppose G inverse is a link, like the logit link or the log link, and you want the Kate on that scale. Okay. So it turns out that then the initial estimate could just be this guy, the initial pseudo outcome. You just estimate the difference in the curve. And then the correction term applying our result turns out to be exactly this term. And using this for the log, logit, and identity link will yield second order bias that is a cross bias term. So it's W robust, just like on the additive scale. On those three scales, it will be W robust. An interesting fact about the quantile treatment effect case is that in fact, you don't get a W robust bias. You do get a second order bias term in terms of the quantile function. So you pay a price in terms of, and this tied to the nonlinearity of the quantile transformation. There's a nonlinearity involved in G as well, but it turns out to be manageable in the case where that link function is either the log or the logit. And in the paper includes, in the appendix particularly, several more counterfactual regression problems that might be of interest. The Kate for the treated, the compliers, and for the overall population in the presence of a measure confounding identified by the conditional Wall estimate. The nonparametric counterfactual outcome mean for continuous treatment, so dose response relationship between a continuous treatment and an outcome under both unconfoundedness or some confounding using proximal or IV identification conditions. And then the Kate using proxies. Nonparametric regression under missing at random and missing not at random conditions. I mentioned one in that example earlier with an IV. There are other techniques known as shadow variables that you could also use for identification, and they also produce a specific set of pseudo outcomes. Let me stop here. I want to thank my co-authors, Elsa and Arun. This is actually one of Elsa's dissertation work, so she should be getting the credit for this. It's really hard work, collaboration, mentored by myself and Arun. And this work is funded by NIH grants of mine. And the paper is on the archive. And thank you so much for listening. I'm happy to take any questions.
So I have a question about, say, maybe two things, and then you have B and X being the same. right? So you have to say, regression. So, I guess under compounding this, you can write basically just the expectation of y given, a equals to 0 and then no. So
Yeah.
you don't.
Yeah, that's a really great question. So the point is, I want the Kate, and the Kate is just the difference of these regression functions. Why not just do the regression functions and call it a day? That's true. That is one strategy. But it turns out not to be an optimal strategy because the behavior of this H hat, its bias is going to be dominated by how well you estimate each of two curves, both curves. Think of the Kate. The Kate is a regression function given X. It's likely to be a lot smoother than the two curves. So the difference of the two curves can belong in a very different smoothness class than the two curves. So if you do the two curves, you might kill yourself, figuratively. No, so the question is, as I understand it is, so let me do this example because it's a familiar one. Is do you need what properties should you have for these estimators? You can use any machine learning tool or any estimator you want for them, provided you use cross-fitting. If you're going to do in-sample, then you need things to be well-behaved and downstairs. So in all the simulation application, we use superlearner, which is, Mark Van der Lens procedure that combines many learners. You can use something else if you want, and we had random forest, the usual things, X booster or whatever they call it. So there's no per se restriction on what you can use. What I do want to say is I actually think that's where you can try to be as adaptive as possible because it doesn't hurt you to be as adaptive. It doesn't hurt you to try to adapt to the data in learning these two objects. You want to attain the best possible rates for them because that will in turn mean that you can ignore their combined bias, which is second order, provided it's second order. In addition, even if it's converged at slow rates, you still want to optimize it because that's going to dictate the rate of estimation of the Kate in this case. So fortunately, you can be as aggressive as you want to. And I say these things, but with caveats, allowing for the sample size that you have. You can't go too crazy if you have a small sample size. But yeah. So the usual statistical wisdom that the more data, the more aggressive you can be, the less data, the less aggressive you probably want to be. Yes, Ellen.
So Eric, can I ask a couple of questions? This is Andrea.
Yeah.
Hi, how are you? So let me see if I understand what you're doing.
Why do we know that such an object will exist?
No.
Yeah.
Let me ask.
So yeah, the point here is that we're not actually requiring that the conditional mean of R given X be pathwise differentiable, because that's not. We're requiring that the mean, note that the pathwise derivative is being taken with respect to eta t, that's buried in here. And it turns out that's a much, much weaker requirement. That's basically what happens. Yeah. Does that answer the question?
Yeah.
That's a good question, yeah.
Can you hear me? Hello? Can you hear me? Hello?
I don't know what R learner is.
Can you hear me? Hello?
I don't think they can hear us.
By who, sorry?
Hello?
Okay, yes. Sorry, there are a lot of names. It's DR learner, X learner, R learner, FW learner. So yeah, that's a good question. There's also a parallel literature where what people do, and I think that's the spirit of what they do, is they say, I want to do a kind of factual regression. But what I'm going to do is I'm going to define it indirectly. I'm going to define it as a minimizer of a kind of factual risk. And then I'm going to estimate that risk with small bias. So I'm going to basically get the influence function of the risk and estimate that and then minimize that. That's a completely different approach because, and in fact, the rates that you get from that approach, as far as I can tell, this was discussed by Ed Kennedy in his paper, where he compared the rates of taking that approach versus taking a pseudo outcome approach, and those rates are conservative. It's much more general in many cases because it only requires you don't need to have an explicit definition of a parameter. You can define it through risk minimization. By virtue of being more general, it's not surprising that it will yield conservative rates. So we never considered it. We haven't considered it at all because our whole philosophy is to go directly for the target of inference. However, just to be fair to them, there are some problems that we can't do. So for instance, the most important one that we just cannot do is non-parametric instrumental variable problem with a continuous treatment and a continuous outcome, because you cannot explicitly write the target parameter as a solution to an integral equation. So you have to define in terms of a moment equation. And they can do that, cannot.
Yeah, super interesting. I have a question about the first web topic we talked about one. My understanding of what you're proposing is that you take your typical food estimator and you make a modification to it and you show that under this modification you obtain really possible rates for a broader class of basic functions than
Yeah, that's good.
Why you might choose to use some class of basic functions that were the confidence under the new theory but were not
Polynomials. Polynomials is the most natural class of smoothers that people use in practice. I want to use in practice. Legendre, what are the other ones? Legendre polynomials. There are a number of types of polynomials that are intuitively appealing. This allows you to use polynomials. The previous one allows you to use polynomials up to a certain point. The second point I want to make, and this is actually, I said it in passing, but to us, this was actually a really appealing property, is this property down here. Our estimator is bounded, which means that you can use a lot of the tools for adaptivity. So cross-validation, for instance, requires, and usually what people will do is they will take their least squares estimator and they'll bound it somehow. They'll modify it, but that may actually hurt the original estimator. They can do it very carefully, but the point is that you've already done the work here. You can just go and play. I don't want to say that they can't do it. They can do it, but they have to be very careful in how they do it. And we're being careful up front and saying, you don't need to worry about it. So and it sounds, there's a little bit of salesmanship maybe in what I'm presenting because I'm presenting our work, but ultimately at the end of the day, there are many examples where it really doesn't matter. There are a lot, I have to be, there are a lot of examples where it really doesn't matter. The simulation I showed you were examples where we think it matters, where you have outliers in your covariates. So in many instances, you might try this, you might try something else that's easier to implement, and you'll be just fine. So yeah. Yeah. So yeah, that's a fair question. I had enough math in there. I decided not to include it. It's given here in a very cryptic way. So let me just try to explain this. So this is the oracle rate for the kate, if the kate is known to have beta m derivatives, and it's in D dimension. Did I get this? Yeah. Okay, so this is what you want to attain. This is going to be the bias. Indicate this bias is the product of the bias of your propensity score and the bias of your outcome regression. As long as the product bias is smaller than the oracle rate, you can ignore having estimated the nuisance function and you attain the oracle rate. Your rate optimal, you get an estimator that's as good as someone who has actually observed the counterfactuals. If it's not smaller order, then this is going to dominate your rate. So there's a different question there, which is, can you do better? There's actually a positive answer to this. Ed Kennedy, Jamie Robbins, and the gang at CMU have a really beautiful paper on minimax rate of estimation for these types of objects when in fact this isn't satisfied. Because this will no longer necessarily be attainable. There's a new rate of minimax rate of estimation below a certain cutoff. And you have to construct new estimators. So we don't have that property. Does that answer your question?
Thank you very much. I have a question on the second, the last time, sure.
Yeah. Yeah. So these are point-wise confidence intervals, I should say. And we're basically using, so there's a literature on constructing confidence interval and confidence bound for the least squares nonparametric estimator. We're using that one because asymptotically we behave the same. So we didn't have to develop any new technology for that. We're just piggybacking on that. But these ones that I'm showing here are not the confidence band, although there are formulas for the confidence band.
There's a question on Zoom by Marcos. So I read that the choice of basis seems to matter more than the difference in performance between SW and OLS. If I understood correctly, do you recommend also selecting among different bases using cross validation?
Yeah. 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 So the choice of basis, like wavelets have these amazing properties of adaptation that Fourier or polynomials don't have. And so we're presuming we live in one smoothness class, but if you want to, as you want to allow for larger classes, then you should use appropriate basis function. And cross-validation would be the right way to do it.
I have no other questions.
Thank you so much.